Are you okay?
Yeah, she's going to bring me a set. I'm just taking this one.
Yeah, that's a good idea. Okay.
So that way
All right.
my cornea is not destroyed.
Yeah, I agree. The dad in me is a little bit freaking out, okay?
No, it's fine. It's fine. And
Okay.
it's just like a...
All right. Well, last time that we were together, we had started chapter 8, which is about, well, it's continuing the ideas of probability. But before we can do this business of continuing the ideas of probability, we first had to know more about counting. And the idea here was not counting as in 1, 2, 3, 4, 5. It was when like there's a very large number of things, where you're not literally going to like make a list of all the possible combinations of 2 cards you could draw from a deck. Okay, it would add up to hundreds. It's not the best use of your resources. Rather, we were talking about counting in the sense of like how we get a number for those sort of things. And the first ones that we had been doing is when we talked about permutations. Now, the permutations meant like as in order mattered. The classic example is books on a shelf. It's like you're trying to put books on a shelf, and you were the example we did the other day. You had 5 books, and you put 3 of them on the shelf, and the order mattered. Okay, so for some reason, like A, B, C was different from A, C, B. Okay, for whatever reason. Okay, or passwords. Just knowing that your password has A, R, Q, and 3 in it doesn't. I mean, the order matters. You're no closer to getting the password until you have them in the right order, right? And so permutations, which your book uses this notation. Oh, this pen is dead. Permutations where they had P, which looks like it's going to be a little horrifying when you think about like, oh, aren't we going to be using this for probability? Well, yes, but then it's going to be 2 numbers separated by a comma, where the first was the number of objects you're selecting from, and R, the second number, was the number of objects you were selecting from that population. Often N and R are the same number. Like you mean, I have 1, 2, 3, 4, 5 students in the room today, and I'm going to select all 5. How many of them, how many different orders of the 5 students could there be? And remember, the formula for it was just n factorial over n minus r, the quantity factorial. I had that right? That's not the one that we're doing today. That was permutations, right? Okay. So for example, if I said there's 5 students in this room, how many different orders of the 5 students could there be? Okay, we're talking about the number of permutations of 5 things taken 5 at a time, which will be 5 factorial over 5 minus 5 factorial. That's 0 factorial. By definition, 0 factorial is 1. So it's just 5 factorials. 5 factorial divided by 1, or 5 factorial, which I think is 120. Yeah, I'm pretty sure it is. If I'm wrong about that. So there are 120 different ways we could order the 5 people, the 5 students in this room. Is 5 factorial? Now I'm freaked out. Is it 5 or is it 60? Wait a minute. Hold on. What's 5 factorial? Can't do it in my head. 5 times 4 times 3 times 2 times 1. That's 6 times 4 is 24 times 5 is 120. Yeah. Okay. So there are 120 different ways we can order the 5 students who are in class today. Alright, so all the problems in section 8.1 come from this idea about permutations. Sometimes it's just a little hard to figure out how. So for example, let's look at number 24, which is the one Malia was worried about. A child has differently shaped plastic objects. There are 3 pyramids, 4 cubes, and 7 spheres. How many different ways can she arrange the objects in a row if each is a different color? Okay, in other words, there are 3 pyramids, and they're different from each other. It isn't like it's a pyramid, it's the red pyramid, and that's the blue pyramid, and that's the green pyramid. So red pyramid first is different from blue pyramid first, is different from green pyramid first. In contrast to if they were all the same shape and color, well, you can't tell them apart. Pyramid would be the first one. Alright, so these are all different objects. There's 7 spheres, 4 cubes, and 3 pyramids. So in other words, there's 14 objects here, and they're all distinct. We can see that they are all different. So, how many different ways could we arrange them? To me, that's it. Am I wrong about this? Maybe other people did it differently, but I would think this is 14 objects, and we're picking 14 of them, and we're trying to see how many different arrangements we have of them. That would be 14. That would be permutations of 14 objects taken 14 at a time, which We already know the pattern here. That's going to be 14 factorial over 14 minus 14 factorial, which will work out to 14 factorial, which is a ginormous number. Is that what you guys got for that one?
Yeah, I just didn't bother with like that second number. I just did 14 factorial.
Right. I mean, another way to, a more generic way to think about it without using the idea, we could have done this problem already with what we learned back in probability. I mean, another way to think about it is that first object, there were 14 to choose from. And then the second object, there were 13 to choose from. And the third object, there were 12 to choose from, and so on, all the way down until you just had one choice left. It's just that we have a more powerful tool now, this idea of factorials and so on. Okay? So part A, I'm not too freaked out about. Part B, how many different arrangements are possible if the objects of the same shape must be grouped together, but each object is a different color? So, what they're saying here is, you've got to have, first the, however many pyramids. So first you're going to have 3 pyramids. And then you're going to have 4, whatever the next one is, cubes. And then you're going to have 7 spheres. But each of those 7 spheres is a different color. Each of those different pyramids is a different color, and so on. So, well, wait a minute. How does this work? How many different ways are there to arrange 3 pyramids? We now know the pattern, right? This is the permutations of 3 things taken 3 at a time, which is going to be 3 factorial, or 6. How many different ways are there to arrange 4 cubes? We now know the pattern. It's 4 things taken 4 at a time, which is 4 factorial, which is 24. And how many different ways are there to arrange 7 spheres? There are 7 spheres taken 7 at a time. It's going to be 7 factorial, which I don't know off the top of my head. Alright. So, we got to pick one of these 6 ways, and then one of these 24 ways, and one of these 7 factorial ways. Well, this is kind of like those tree diagrams, right? First you pick one of those 6 different pyramid combinations, and then whichever of those 6 different pyramid combinations you pick, you've got 24 different cube combinations, and then for each of those 24 different cube combinations, you've got 7 factorial ways you can go from there. Well, like those tree diagrams then, it is, you have 6 choices, followed by 24 choices, followed by whatever 7 factorial choices are. And it's a big number, although nowhere near as big of a number as part A. How about part C? How many distinguishable ways can the objects be arranged if the objects of the same shape are also the same color and don't need to be grouped together? Ah, crap. That's a hard problem. Let me think about that. So in other words, we can't tell the cubes apart. We can't tell the pyramids apart. And we can't tell the spheres apart. Now, I remember, this is in the book. And it is not well explained. It is hiding on page 358, just below try your turn there, at the middle of the page. If the n objects in a permutation aren't all distinguishable, that is if there are n1 of the first type and n2 of the second type and so on for all the different types, then the number of distinguishable permutations is, and then it has a formula. Why this isn't in a green box like every other formula in the book, I have no idea. Okay? But what they're going for here is, instead of thinking about this as 14 different objects, think of that as this is n1 equals 3 of this type of object. This is n2 equals 4 of this type of object. And this is n3 equals 7 of this type of object. And then this formula then says there are 14 possible combinations divided by 3 factorial, 4 factorial, 7 factorial. And then it's just a whole bunch of math to get there. I am a little frustrated that that's not highlighted in clear. Okay? Malia, was that the kind of problem that you were getting hung up on?
Yeah, I just didn't understand, like, even from the first one, I
Okay.
wasn't sure if the question was, like, every single piece was a different color, like, within the shape, or if, like, the shapes were a different color.
Oh, okay. No, but like there was a red cube, a blue cube. Yeah, okay. All right. Well, I think this gets us on the road. I mean, the other parts of the problem, 24, are just more examples of like these kinds of exercises of rearranging it and so on. Did you have another part of it? Or a different question?
No, I was gonna ask about the Easter.
Oh, please, of course. All right, well, she hits up. We're just going to go ahead and pitch this pen that is obviously dead. All right, tell you what, while she's up, I was going to move on, but why don't we go ahead and do another one while she is out? All right, let's actually go ahead and do 24D. 24D. In how many ways can you select 3 objects, one of each shape, if the order in which the objects are selected does not matter, and each object is a different color? I don't like that one. In how many different ways can you select 3 objects, one of each shape, in which... Oh, good lord. D and E are way too hard. Did anybody get D and E to work? Oh, you wouldn't know because you don't, it's an even-numbered problem. Okay. These are some seriously advanced counting type problems here. In how many ways can you select... I didn't realize how hard... I mean, when I was scanning this, just looking at problems on the homework, I didn't notice how hard those 2 were. In how many ways... On the other hand, what big kids you are to be in this class. So, if you didn't know, on Friday, I was up in Indianapolis for a conference about the quantitative reasoning class. And our quantitative reasoning class here is, well, I don't say it's pretty good. That sounds like a bad thing to say. What I mean is, they learn a lot in that class, and they're good students. Does that make sense? I don't mean it like I said, oh, that's pretty good, whatever. No, I mean like they're working hard, they're doing a ton of stuff, etc. But in some school districts, the quantitative reasoning class has kind of become where they dump people. You know what I'm saying? You hate math, you're no good at it, just take this and don't fail it and we can graduate you. And so, like, so many people who were at the conference were like, I'm so jealous that you have these good quantitative reasoning students. And then I was like, yeah, they're doing great. I mean, all my students are doing great. The students who are in Finite Math, they're doing great. And they're like, what? You get to teach Finite Math? That's like the coolest, most practical class, and you guys, they cover all kinds of interesting, challenging problems, and they're like the best and brightest. I'm like, I know. They're so good. I'm so happy with them. Anyway, so yeah, they were totally jealous of my quantitative reasoning students, and then when they found out I also had Finite Math students, they were like, unhealthy jealous.
When I hear quantitative reasoning, I just think that sounds so hard.
No. Honestly, a lot of it is very similar to what you guys are doing. It's just somewhat less
In depth.
Yeah, even less depth. It doesn't quite go quite as far. They didn't do the linear programming thing that you guys did at all. But like they do probability, they do permutations and combinations, what we're doing right now. They just don't necessarily have as difficult of problems, but they also cover more different things. I mean, they also did things like tax schemes and finance, like mortgages and stuff like that. They also do stuff about like a lot more about units than you guys do. I mean, they're just 2 different classes, okay? But in some school districts, they kind of have made quantitative reasoning you have to take something before you leave here. That's how it works, right? Because you basically have to take a math class every semester you're in high school, right? And so, yeah, some of them are not so great. Some of the school districts, their quantitative reasoning classes kind of where like people who aren't passing things go. Anyway, but that is very much not the plan here. Because everybody passes because you're all really good students. All right, so let's not stress out about D and E. Those are actually pretty darn complicated problems.
Yeah.
Okay. I mean, I will spot check. I'm not going to get too stressed about it because those are too hard. All right. We are actually covering sections 8.2 and 8.3 today, partly because 8.2 is just such a tiny bit of material, And 8.3 puts it all together and does something with it. So we're actually going to do just a handful of problems from each of those. We've kind of alluded to this business of what's going on in 8.2 already. And this is this business of combinations. Combinations is very closely related to the idea of permutations. Permutations was when the order was what mattered. Like a combination lock. I'm sorry. That's exactly the wrong example. Permutation when the order matters, like a password. Even if you knew all the letters, if you don't know them in the right order, you still got nothing on a password, right? Passwords are about permutations. Combinations are when the order doesn't matter, which is why the word combination lock is stupid. Because a combination lock, the order matters, right? If you turn your right to 23, left to 18, and right to 12, but that's the right numbers, but not in the right order, you still got nothing, right? The lock is not going to open. A right word for it would have been a permutation lock, but you know, whatever. Combinations when the order doesn't matter. And the example that we used in class the other day was pizzas. It takes a serious pizza jerk to say that the order on the toppings matters. If you're ordering a pepperoni, sausage, and mushroom pizza, and it has to be in that order, you want the pepperonis on the bottom, then the sausage, and then the mushrooms. You don't even want to know what the delivery guy's going to do to your pizza, right? If you think a pepperoni, mushroom, sausage pizza is different from a mushroom, pepperoni, sausage pizza, they're not going to be very happy with you, right? If the order doesn't matter, then what we're talking about is combinations. I pulled 2 socks out of the drawer. There's red socks, blue socks, and white socks in the drawer. What did I get? You know, like I got a red one and a white one. Those are combinations. It doesn't really matter. I pulled this one first and then this one. Okay, I reached in and I took 2 out. Combinations are when the order doesn't matter. And unsurprisingly, there is a formula for it that's not terribly exotic. It's written in kind of a weird way, again, just like our permutations were, where you're picking from a set of so many objects, and you are picking so many of them. Yeah?
This is 8.3.
This is 8.2, I think, actually. 8.2 is combinations, isn't it? Yeah.
I thought we just did it in picture.
Yeah, and then we're going to use permutations and combinations to do 8.3. So there's really not much of a thing here. It's just a formula. We have this. We tried to solve as long as we could. You've only missed about a minute.
Oh, that's fine.
It's okay. All right, so combinations is when the order doesn't matter. That's kind of the opposite of permutations. But the formula is alarmingly similar. It is n factorial over n minus r, the quantity factorial, divided by r factorial, also divided by r factorial. Notice that it is really, really close to the formula for permutations. In fact, the only difference is that r factorial in the bottom. Notice what that means. You're dividing by more. Right? The denominator is bigger here. So there's always fewer combinations than permutations. Right? I mean, if I'm picking from 5 books, remember the other day we did this? We had algebra, biology, chemistry, Dutch, and English. Okay? And we only picked Dutch because I needed a D. And you're picking 3 of them to put on the shelf. And we were playing this game, well, A, B, D, ABC was different from A, C, B, which was different from B, C, A, which was different from B, A, C, and so on. Those were permutations. Combinations, what we're saying is just pick 3 books. I don't care what order they're on the shelf. Then all these 6 possibilities, I didn't list them all here, all those 6 all are the same thing. They're all the same combination, right? So of course there are always fewer combinations than there are permutations. Same with like, how about Subway sandwiches? That's a common one that is on those kind of problem sets, you know, on like standardized tests and so on. They'll say, all right, you know, we've got all these toppings. You know, we've got lettuce, and we've got spinach, and we've got bell pepper, and we've got banana pepper, and so on. But the order of them, I mean, if I tell you I want a sandwich with lettuce, cucumbers, spinach, and bell pepper, I don't care the order they're put on, right? And so, again, it's just the combination that mattered. I picked 4 toppings from the 12 they offer. Okay. So in and of itself, this idea of combinations isn't really all that hard. It's mainly just keeping the formula for combinations separate in your mind from the formula for permutations, because they're very close. By the way, just as was the case with permutations, it's got those factorials in there, and n might be a pretty big number. I mean, I don't know, if we're saying at Subway, we want to pick, let's say we're going to pick, how many combinations are there of the 20 condiments, or whatever the right word is, the things that for making your sandwich, we're going to pick 4. This gets pretty big pretty fast. I mean, that's going to be 20 factorial over 16 factorial times 4 factorial. 20 factorial is a really big number. If you sit there and plunge into your calculator can probably do 20 factorial. I don't think it's like into the range where like it's more than it'll overload your calculator. But it's a big number. But you almost never compute factorials bigger than about 4 or 5. Most of the time, the trick is to recognize the pattern, that this is 20 times 19 times 18 times 17 times 16, 15, 14, but wait a minute, that's 16, 15, 14, that is 16 factorial. And you've got a 16 factorial in the bottom. So you just cancel those out. Right? You very rarely ever actually compute a factorial bigger than about 4 or 5 factorial. Most of the time after that, they're in a ratio, and it's more a matter of figuring out what to cancel. So now you've just got 20 times 19 times 18 times 17, whatever that is. It's not going to be a small number. And then divide that by 24, because that's what 4 factorial is. And you'll have your number. It'll be a biggish number. I don't know, a couple 100,000 probably. But it is not, you know, like 10 to the 57th power kind of big, right? 20 factorial might be. 20 factorial might be something very large. All right. Once you have these two ideas separated in your mind, then you just can solve problems with them. Because remember, the whole point of this was that we were using these to count things that were too darn hard to just make a list of. I mean, it's not that it's impossible to have made a list of all combinations of 4 sandwich toppings from the list of 20. It's that it's a few 100,000, right? I don't want to really sit there and go, lettuce, spinach, tomato, pickle, lettuce, tomato, spinach, cucumber, lettuce, tomato, spinach, bell pepper, lettuce, tomato, spinach, banana pepper, and just keep going with all these combinations for a few 100,000 of them, right? This is counting in the sense that we found out how many there were, what the cardinality of the number of sets there were, without actually doing it all. Alright, well then we can use that for probability, because remember, probability was usually just like the number of ways it could go right divided by the number of ways it could happen. So for example, if I'm going to pick from my 5 textbooks over here, and I'm going to pick 3. There's 5 textbooks in my book bag, and I'm going to pull 3 out. What is the probability that I'll get biology, Dutch, and English? Well, that is one combination out of however many. There's only one way it can go right. I pulled out biology, Dutch, and English. Out of all the combinations that there could be, well, how many combinations are there? There are combinations 5, 3, which is 5 over 5 minus 3 factorial times 3 factorial, or 5 factorial over 2 factorial times 3 factorial. All right. Well, that's 5 times 4 times 3 factorial over 2 factorial times 3 factorial. Cross these 3 factorials out. That's 20 divided by 10. There's only 10 ways it can happen. There's only 10 different combinations of pulling 3 books out of your book bag. So, only one is right. Only one of them is biology, Dutch, and English out of the 10 ways it can happen. And that's the probability you'll get the right combination of 3 books. That's all these kind of problems are. They're just a way, we did probabilities like this before. They were just things we could either make a table or count on our fingers. We were counting things like how many people in the room are wearing glasses out of how many people there were in the room. Oh, yeah, that wasn't so hard, right? Now we're just talking bigger numbers because there's more possibilities, right? A classic problem. Somebody called in order to a 2-topping pizza, but we lost the order. What's the probability we'll get it right? Okay, so let's just say the pizza place has pepperoni, sausage, mushroom, hamburger, and pie. I'm trying to think of something, and a topping that also has another letter. Tomato. These are the only toppings we have at our pizza place. All right, and we know they ordered a 2-topping pizza. How many 2-topping pizzas are there? That's the number of combinations of 5 things taken 2 at a time. 5 things taken 2 at a time happens to work out to 10. Isn't that weird, by the way? Wasn't that also 5 things taken 3 at a time? There's a pattern here, but it is something we'll discover later. And so, we know they ordered 1 of them. So there's only 1 way it could go right and 10 ways it can happen. So there's a 1 in 10 chance in this case that we got the right pizza. Okay, that's not very good answer. You should really call back and say you lost your order. And no place only has 5 toppings, right? All right. So that's what these things are. All of these problems are really just more applications of what you did in 8.1 and tying it back to chapter 7. It's just a matter of remembering, is this a combination or a permutation problem? Because they generally won't tell you. Well, they're kind of telling you. I mean, they're either going to explicitly tell you the ordering matters, or the wording will tell you, you can kind of work it through. So there's really not that much new here. That's why I wasn't really all that worried about combining 2 lectures into 1. I thought there was other things we could do later in the semester to spend more time on. All right, so you probably don't want the pre-calc assignment. I'm wondering how we are on. Oh, there it is. Okay.
Yeah, we didn't have an assignment in pre-calc, did
Aside from the one that we...
The one that we signed back on like the Monday before, like a week ago,
Right,
yes.
right.
But nothing new, because you guys did speed dating while the other ones went to the BSAT, right?
Right, yeah.
Okay. Speed dating. Yeah, we did speed dating.
And it wasn't.
Did anyone find their lover?
What did you say?
Did anyone find their lover?
You'd have to talk to Ashton. I don't know.
I wish.
Anyway,
Ashton found his lover.
I don't know.
That's surprising.
Anyway,
You know what?
no, it was just an activity. It was actually a pretty good activity. It's just the problems were too hard. I feel like if the problems had been easier, it would have worked better.
They were good homework assignments.
Yeah.
I don't know, the girl with the messy handwriting was pretty cute. It's fun.
Whatever. I don't even know. Anyway, so for the next time, you actually have problems from 2 different pages because, of course, we're doing 2 different sections here. So this first one comes from section 8.2, and it's mostly just sort of cranking them out just to make you very fluent at how to do combinations. And then the second one, which comes from section 8.3, is on page 378, and it is problems 1 to 22. I realized there were so many. 44 and 77. Let me just take a look here. I'm wondering if that was supposed to say 12, because that seems like an awful lot of problems. Hold on.
So wait, what does chapter 8.3 cover?
8.3 is just it says probability applications of counting.
Oh.
So you're using permutations and combinations to come up with probability problems. Yeah, okay, I do remember this now. 1 through 22, very few of those problems probably require, well, some of them might require some work. Like, as in, like, a lot of them you can just write the answer down. Like, there's no work to show. But some of them would. If it's radically too much, why don't we get started on the homework today and see how it's going? We might carve that down a little bit. Okay. All right, let me stop the camera here, and I will entertain questions as you guys work on it.